Good afternoon, everyone. It's my great pleasure to be here, and I hear that my talk is 10 minutes shorter than I had planned. So let's just as I go. So I'm going to talk about something that really excites me because I really like building stuff myself, and often I miss tools for building things, and hence many of my research is motivated by that. First, I should introduce my research team. This is slightly older. Martin, since then, has moved back to Vienna, working again with Helmut. And in this talk, I will talk about work done by many of my students and postdocs in my group. So as Tom was talking just before this, that we have large collections of data, we have images, and we have model collections. And I think this is really exciting in the sense, now with all the data, we can create interesting links. We can link the images and 3D models, and this allows very novel types of interactions. So here, as you see, there's an image collection and a model collection, and that 3D model is linked back. I skip all the analysis here, and it retrieves all models with similar views. So all images with similar views. So there's a pose estimation. So you can click that dial, you get different cars. But not only that, because images and shapes are now linked, you can freeze a model and then try to change the shape. And it retrieves images of cars of the same view, but flatter and longer, right? So this is very interesting avenue that we didn't have this option a few years back of linking these data collections. So a large part of what we do in our group focuses on this topic, right? That's not what I'm going to talk about today. Right? So what do we do if we don't have data? Right? And we have all the talks that we heard today morning has data in some form, right? Whether it's data collected of sound clips, or of 3D models, or of scans of cities, etc. But I'm also interested in creating new shapes, right? And by definition, these don't exist, and data-driven fails in a way. So the way we can attack this problem is bring in priors, and sort of Tom hinted at these priors. And there's different sort of priors that we could think of. Some we thought of, and some others in this domain. One of the strongest would be physics, and I think Ethan is going to talk more about that today or tomorrow, I forgot when he's talking. Or when we talk about objects, they have certain functions. So if you know what it's going to be used for, that can play an important role. And also how they are going to be manufactured or created. Now, this is a common story in computer graphics now, that we have great devices for acquiring, but we have many desktop solutions or much cheaper solutions for creating. So this is just 3D printing, but there's laser cutting and other sort of scribing, etc. And this has opened up a lot of these tools to the users. And there are various communities, I don't know how many of you fall in any of these categories, where people have bought this or have access to these devices, and they want to build things because they want to build new things, right? Now, these can be occasional users, like like us. You might work to do something over the weekend, or you would put in a bit more time, and you have a passion for creating some hobby that you want to have, or you are professional and dedicated for this. And hence, their skill sets are different. Some would sketch, some would use modelers, or if you're a professional, you can go and take a course for 2-3 years to learn Maya or any of these tools, right? So their skill levels are different, and the tools they have are going to be different. And a thing that should not be forgotten, that often they need to communicate across each other. So for example, if you want to if you're planning to build a new house, you would go and talk to the architect about your requirement, and the architect would talk back to you of conveying the design. Right? So let's see how a typical product design cycle works. So this is from Anvil. So one of the first things is creating this idea, right? So having an idea, and this is from involves sketches or prototypes, and you come up with the product. Then you do this. This is very iterative, so this is the next step, which is the iteration step. And then you create some actual prototype where you see if it actually works. So in this case, what's important is when you hold it, can you still access all the buttons, because that's important for playing this. Okay. Finally, the system. Now, the type of instructions that are available, the YouTube is a very good source for this, and there's also very interesting design books out there for creating this. And the type of objects we'll be focusing on will be toys, because that's quite interesting. We'll be designing of workspaces, and also functional objects like bicycles and other things, and gym machines, as Tom showed. So let's list what are the main design challenges in this area. How do you express a design concept, right? This is the first thing. How do you get out your idea onto paper? Then how do you convert from that sketch to a working model? Then when you want to actually build it based on whatever you have chose, what are the fabrication constraints? How do you adapt it? And an interesting question is, how do you explore the space of possibility that all these constraints allow you? Okay? And always the designer will choose. It's not an optimization that gives one output, right? It's multiple one. So I focused this talk on 3 aspects of this, in a way. One is, how do we guide the designer? Then how do we interpret input, which is not quite precise? And how do we make stuff? Okay, so let's just start with the first one, which falls under how do you explore the design space? Okay. Now, this is a common problem that is, I think, not quite well understood how to solve yet, which is you are given a problem setup. So in this case, it's an arrangement of elements. So you can see there's arrangement of elements. You can see some arrangement of elements. And the user comes in and makes one change to one of them. And you want to find out what happens to the other elements. Like, this is a very classical shape editing problem. But what we want to come up with is not one answer, but a series of answers. So if you think about what the answer would be, or you would like to have, you would have different interpretation based on how you have organized the arrangements on the top in your head. Right? So these are different arrangements for this. Right? So here you say that all of them got rotated. This was rotated by different one. You can have the lights now. Oh, I see. Or there are different variations, right? So the entire goal of this work is how can we allow to explore the space of variations. And this is really recent work, so we're quite excited to see more in this direction. Okay? So what are the current tools for doing it? So if you're using Illustrator for doing it, for changing this edit pattern, maybe you want to give it increase the negative space, this is how you would do in Illustrator. And those who work for deadlines, this is probably a familiar experience when you are trying to arrange this. And the reason is we are working at the wrong level of abstraction. We are working at the level of elements. So what we propose is you make one change, and it suggests different change of the whole arrangement. Right? And this is the interesting bit. And you can select on one, you like that arrangement, and it keeps going up. Now, this is quite attractive in the following sense. It vastly simplifies getting to one. But I think the most important thing is it moves you away from a fixed representation. So you could have done the same if you had a procedural model of this. But what we are proposing is not have a fixed model. The model sort of adapts as you go along, right? So I think that's very interesting. So, and this allows you to get out of this bottleneck that you get hooked onto a particular design, because that's what you have created. But there is other ones which are possible around that. So let's try to model this problem. So what we have is an arrangement, which is quite simple here. And I would like to abstract it, and we saw it already in the previous slide. So we can create a graph where a node is an element, and the edge denotes the relation between them. Note that the node can also be a relation, because we have the second level of relation, so higher order. Okay? So for this example, the golden one are the elements, which is quite simple. And then this blue one denotes a relation between two golden elements. So there can be different elements. And the green ones, the green nodes, denote a relation between relations. Okay? So that's how it is. And these are typical relations that we consider in our case. For example, if you look at the icons on the left of the different sponsors, you see that they're regularly spaced, they're aligned, they have regular spacing between them. So that's an example. So I'll go along introducing some notations. So we have a pattern given, and we abstract it as a regular graph. But it might seem a bit confusing because we thought we want to get away from a particular representation, but now I fix one representation. But what you would see in the immediate formulation, this is a superset of representation. We would take subsets of this, and I will make it more clear. So how is the user interacting? The user is interacting a couple of nodes. In here, he or she has moved it here, and all these red edges gets affected. And then now the goal is what happens to the rest of the arrangement. And these are different changes that are possible. And there are three types of changes. You can keep original relation. You can change it, as in you keep that they're going to be equally spaced, but the spacing is changed. So that's what I call change. Or you can completely discard this relation. Right? So for each relationship edge, you have three possibilities. So we are talking about a 3n, 3 to the power n space exploring. Okay? Now, I'm going to introduce some notation, and hopefully this will be clear. So an arrangement I would consider as an arrangement of element where each element has, this is in 2D, has a xy location, a theta, and a scaling. So that's a change you can do. But strangely, I will also encode the relations. Right? And as you see, this is overcomplete, because if you have these specified, the relations are automatically specified. But as you see in the formulation, there is a reason why we keep both of them, because that makes it easier. Okay? Then we have a delta E, which is how things have moved. This is if you imagine one element was moved to another one, so that's a delta E. And this assignment vector, which I will talk about, which consists of how the relations change. So either we retain the original one, or we change them to new values, or we completely drop them for each variation. So that's a formulation. Now, since we have this more variables than we need, because we have relations and we have elements, we need some constraints to make sure this is a valid arrangement, because we have to make sure that the relations and the elements agree, which is encoded in this form. Would not go into the details of that. And we also want to make sure that the edit is satisfied. Right? So these are subject to these constraints. This is a technical detail, but it's important. Okay? Now we have these three notions of valid, which is the subject to a constraint, the diverse, which is the most critical one, and the intuitive, which we don't have a good solution, and it's heuristic solution for that part. So what do we mean by diverse? So among the set of arrangements which are valid, that means the elements and the relations agree, often they are just a rigid transformation of each other. So we don't want to show the identical patterns many times to the user. We want to show a diverse one. Okay? Let me play this video. So the user edits one. This is a set of arrangements that you can have. Many of them you would see. Sorry. Yeah. So these are more or less similar copies, and these are not very intuitive and should be left out. So we want to get this. So the idea is, how do we get a handle of this diverse one? So let me reintroduce the problem. So we are trying to minimize these two errors, the validity error and how close we get to the edit metaphor. And we have this, these two error terms that I showed. And here, all it says, because I did not introduce all the symbols here, that the original relations are preserved, if you have that set, and the changed one have been met to the final target. These are the red edges we had. And there is some regularizer for the problem. Now, the main insight here to keep it, to solve this, or address this nonlinear optimization in real time is an old trick, which is doing a linear approximation. So what we do is, we have this set of assignments, and we do a Taylor expansion of the first order here. And then we want to see what's going on. So these terms are important. So this term is after the user has edited. Now, once the user has moved an element, the term has been violated, right? The relations are broken. That's why we have a term here, which is non-zero, because the constraints are not satisfied. So now we have to change the free parameter such that you can restore it, right? So this is what is being optimized. And what do we want to optimize? The residue, because we have the minimum, is back to 0. So we want to set it to 0. And then we come to this linear system where the interesting thing is all the part on the right are known, so you can solve for the mu that we need to adjust elements from. And this one depends on the current position, which is good because I don't need to know the changed one to compute this inverse of the Jacobian. Okay, so let's see how this approximation performs. So you have this edit, the golden one is removed. And the visualization is the blue backdrop you see is the actual approximation, and the black lines are the other way. So the blue one, so the blue one is the actual solution if you solve the nonlinear one, and the black one is the approximation. So this is good enough for us to do the diversion. But you see for other ones, I'm sorry, the board is a bit clipped, but you can see that the one has been tilted. So along these ones, the approximations are good. But here, where there's accumulation of rotation, the approximation is bad, which should not be a surprise because we just did a first order. Okay, so there are some implementation details. So now we can detect these distinct clusters by doing a clustering not on the element level, but on the relation level, right? So that's very natural to do. We have some regularizer and some extensions that I leave out for this talk. Okay? So let's see how the interfaces. There are two interfaces. As you edit, it will show you these multiple variations, or you can show it directly on the screen. And it's best to just show these videos. So you change one element, and all the other gets rearranged, and we are showing top 8 out of those. Note that the neighboring one are distinct, because this is one of the things we had, and this is a screen capture at real time. And then you edit again, and then the next row appears, because you can always backtrack. You can go further and pick another one. And if you look on the top, it says computing solution and updating display. These are vector graphics underneath, so it turns out that displaying these vector graphics in MATLAB is more time-consuming than actually solving this linear approximation. Note that these are all the linear approximation. Once you click, then you solve the exact one for only that instance. Right? This is showing only the top 8, but you can have a lot more. And this is my favorite, this type of interface, where you change, again, one element, and these sort of red dots appear, as you'll see, once you change enough. And if you move your element, it shows the whole arrangement where it goes to. Right? And this is very good, which is very good if there's a fewer number of variations you're looking for. If it's 50, then there were too many red dots, and it's not very useful. I think this project sort of originated from these years of painful Illustrator experience where you change something and the whole structure is broken. You have to regroup and ungroup and all these things. OK, so the main message here is that it's very interesting to try to look at the spatial variations to get me or get us out of this, that you're hooked to this particular relations that you have noted, where there is these nearby arrangements that are possible that are different sets of relations. And we have explored it in 2D, but you can actually do it in other dimensions also. As you noted, we cannot add or remove elements, because that's not allowed in our thing. And of course, the linear approximation we talked about. OK. Now, I think it's best, instead of me rushing through the talk, I would skip almost all this sketchy input part and show just one video, the final result so far. the latest from this year, where the idea is how you would interpret sketches on a single photograph background based on constraints extracted from the background. And as you see, the user is drawing in 2D directly on top of the photo, and these are different interpretations of the sketch as it arrives. Right? And I did not talk about how this is done. Okay. And this is quite interesting and quite useful, and I used part of this tool for designing the kitchen in our place, because you took a photograph, you could design on it, and you get the interpretation and go ahead. Okay, so I will move on. So I skipped one bullet. I think that would save some time, and we can focus on the interesting one. Now, the third one is when you actually build certain objects, right? These are some constraints. And there's a listed. So we are talking about the trade-offs that are coming from how these are going to be built. And this started, I think, in 2009 or 10 when I came across this book. And those who are from US probably have seen this book. This is a really amazing book. And it led to a series of projects where it really got me thinking, how does things work and how do you convey to others? Okay. And then we had this fun project that when you start with an animation sequence on the person, this is just a motion capture, can you create an assembly sequence with laser cut parts so that you can create this, right? And the answer is yes. You can go to the frequency domain, do some analysis, and come up with these gear assemblies and with how they are connected to get here. Okay. Now, this was very cool. I think this looks really nice, and there's a motor at the top that rotates it. Everything's good. But it got us thinking that can we go beyond this? Like here, if I show this result, you said, oh, that's very cool. But if I think long enough, I would be able to come up with a similar solution, right? It doesn't extend what you can think about in terms of a shape. Okay. This carries the story forward. So this is these are images of origami. Like, so you take paper and you fold it, and this is how you have. And this is what are called straight fold origami, that the folds are done along straight edges. So you fold, and I am sure all of you have done some variants, and this is more or less a solved problem because of this Robert Lang's tree maker software, so you can input of certain thing, and it gives you. Now, one fundamental thing that simplifies this problem is the instructions are you fold, and then you fold, then you fold. It's one fold after another. But then in 2008, with Martin and Elmwood and others, we did this paper on curved fold, which is given a straight piece of paper or sheet metal, you can fold it so that you come up with a 3D shape. There's no cuts, it's everything. So which has incredible fabrication advantages that you can do. Now, these PDFs are available on our website for since 2008 of these folding patterns. So you can download and try, but if any of you have tried it, it's very, very hard to do it. Like it's incredibly hard. And the reason is, if you see here, this is one with curved fold, is it's no longer one fold after another. You have to fold it all together. Okay? And that's why folding these ones are difficult. Now, in this paper, what we had this final shape, and we had the planar one. It didn't tell you how you could get from one to another. And some of these things, of course, Martin can fold all of them. Some of them, after a few years, I can still not fold because it just doesn't come out well. So we thought, can we be lazy and have other ways of solving it? And this led to this interesting variation of if we are given so the problem, now we get to the problem formulation, that we are given a planar sheet with these lines. The color denotes if it's folded this way or this way, mountain or valley. Find out the folded shape, so this and this, and more interestingly, as we will show, come up how to fold it. Right? So it's not the final shape, how to fold it. And this how to fold it links the actual physical realization. Okay? So I'll just try to show it here with this slide. I'm not sure if I can show it. Let me try. So if you see here, this is how it folds. Right? I should have been more careful. I got up a little early today morning. I was trying it. I spilled some coffee on it, so it wasn't very good. OK, so what are the challenges? What is the final fold, and how do you fold it? Now, we are not aware of many people who have tried solving this instance. This is one that we know from a startup, a RoboFold in London, where they try to fold it with a robot. So you have to come up with this whole path for each of the suction cups, how you hold it and fold it. So we wanted something easier and simpler. So what's the problem? We are given a shape. This is not the shape, the input. And then you come up with a series of shapes. So introduce this time element. So U denotes the time, which is how it folds as it goes along. And if you think of in an abstracted shape space, what we have is we have the shape space, which is the condition that these are developable and they should not stretch. And then we have a path, which is given by this. So this top S is this path. As you move along, the shape is folding. So this one, this is the starting shape, and this is the folded one. If you go along here, and the sequence, how we got there. Okay? So that's the orange one. So that you can compute. And now the goal is, can we approximate this path with something that is simple to use? And if you noted how I folded it, I have a series of strings that are attached to it that allows it to fold. And now the folding now amounts to just pulling at this one point. Okay? So the problem is quite simple, at least apparently simple. Which are the points to connect and how to connect? Right? Now, once we have the path, this is one path. I'm skipping over some details. It gives you a vector field at each time instance, because you know which shape it goes to, and these are denoted by the orange one, like how you should squeeze it. Right? And the idea is, now can I come up with a network of strings that helps me to sort of guide it there? And that's the only thing. At one point, I'm going to pull it. Now, this turns to be an interesting problem, which is the following. So you can look at these modes, which we call these actuation modes, which means if you are given a particular string, S, and you shrink the length of the string, which is the delta S, how does the deformation, what are the deformation at each point? So if I take these 2 points and do this, along this one, how does the whole string change? And that defines a vector field on the whole one. And this is on the tangent manifold you can see by the green line. Okay? Now, we have another path, which is the orange path, and our goal is to represent this orange vector in the linear space of this. Okay? And one way to imagine, and that's how we came up with this, why this would be possible is the following. I'll try to explain. Imagine there are 2 strings here and there, right? 2 strings, and we are saying you can express it as a linear combination of this movement and this movement. And if you think about this, since the total string length is coming down, you can again do a Taylor series there, and up to first order, this is going to be good, and hence the tangent plane. Okay, so that's all good. So at each time instance, I have these. This orange one is coming by the folded one, and the green one is by the possible strings we are calculating. And then once you see this version, then it's easy to imagine the formulation we are trying to get. We are trying to have a small number of modes which are given by these lambdas that expresses this, right? So you can do your L0, and then you go down to your weighted least square for solving it. Now, so I should show some result for that. So here, this is for this structure here. You see here, this is just a square. And there are these different strings, and I will show you one mode. So this orange denotes the deformation. And here are the different modes. So I'll try to explain. So this is easiest to explain. You see these 2, and you push. I'm showing the 5, 6 is symmetric. So what it means is, if I just push this, what is the deformation? Right? So that's 5, and these are the different ones. And the goal is, can we express this vector field in terms of this? So that's good. Now, we're almost done. Not quite, because we were stuck for a while on this. So this gives us a solution at each time instance. But now you have to do this for different samplings of time. But the trick is we want to use the same string series, so the same actuations. Otherwise, it would not work. I can't switch strings as we go along. And that formulation gets, so this one should be expressed in the same basis or the same strings. I can't have different along. And this can be nicely encoded by this term where we have decoupled into two variables, psi and lambda. And then it's very much similar, except if you look, the psi variable is shared only from 1 to m, so 1 for each time instant, which is this consistency condition that the same strings are used. Okay, so now for the fun part with some sequences. So this is getting the orange path. There's no string so far. This is actual sequence, a recording of it. This one is easier to show. So you see here, I hold it, and this is the string sequence, right? So I pass it around and try not to hold the block the hole as you go, and you can try it. It's okay if it gets torn because this is simple too. Okay, so some implementation details. There are a couple which is quite important. This one, anyone who's working in shape deformation should be able to guess what's going on there. The self-intersection we need to resolve as we go along, and this comes to an inequality constraint that is dynamically detected. It's also good. Now, remember the self-intersection amounts to that one surface should remain on one side of it. So it's an inequality constraint. I will come back to that later. So this is called the Asimov Chair. We found this model on the web, and this is the final solution. And it's easier again to see in the video. So this is, you see this yellow line with the 2-1. If you look for in a few weeks in advance, we will have much nicer renderings. We were focusing on the method so far. So you see this straw here. I will discuss about that. Again, always the pulling is from down below. Right? And this is not with paper. This is like a foil, a tin foil, or one of these things. And this straw is just preventing it from going down. It's just keeping the height constraint. And again, this is handled very much by the sidedness constraint we had. Okay? We had to build something for the department, so we built this. This is screw motion from the top. For those who know our shadow art work, this one does cast a UCL shadow at some point of the day. These are two examples. So one I showed, the one here, again, this is with the foil. With the foil, it's best to have this sheet. So this is on a table, we put a hole. So this was in between two tables. And it sort of has to go in. This is really nice. And the next one is we were surprised that it actually worked in real life. You'll see this. So this is the Nautilus. This is a fairly big one. I think it's about 2 meters span in one direction once you see it. So there's a few chambers like this. So this goes on till about, I think, 1.52 meters, yeah. I was worried about Martin's finger because it requires a lot of pulling. You can have it go down to a single hole there. That's also fine. It doesn't look so interesting yet, but it will get once it comes together. So this stringing goes through here, and it's harder to show in the sequence. And so this is when it finally wraps around. So you will rotate it, as you will see. And here, you can see it did not lap over, which it should. So you see that it got under. That's why it prevented it. And you can see that we ran out of proper paper size. So these are just paper strips glued with these tapes. You have it. And it can give different solutions because all of them are valid, and some are easier than other because of friction and other constraint, which we don't model but is automatic in a way. One very, very important thing about the algorithm is there is no. You can think the first thing we tried for a long time is make things synchronous, but now the synchronous part comes automatically because the threads are coming to one point. So the adjustment is automatic. We don't have to need a complicated mechanism to do it. Okay. So this is the theme we talked about. We missed some of the part because I did not have the time for that one. And these are the 3 main papers I talked about, rather 2. This I wanted to talk about, but I couldn't get to talk about. And I strongly encourage you to visit our webpage because we try to make all code and data available. This one is not yet available, but both of these are very recent, but should be available in a month or so. That one, we are hoping it would get to some Illustrator plugin or something like that later on. And that's mainly what I wanted to talk about is how to create shapes when there is no example to go ahead with. But of course, we need to regularize the problem, and we bring in other motivations of how you can actually solve the problem and get some inspiration. And what is extremely important is, I think we have this notion in design that often we want to do what the tool allows. But it's good to know the boundary because then you can really stretch it and design tools. That's how many of this research came along, that we really wanted to do it, and we felt that the current tools are not good enough or doesn't support, or I'm not clever enough to use them. So can we have other mechanisms to solve it? And this, some of them have a very long history, some not so, and I think it's really exciting for us to work in this area. Okay, thank you.